graphs. So please do that. So now,
so our first talk today is by Professor Tara, Cambridge, a perfect transfer of quantum information across graphs.
Well, not a professor. But anyway, thank you very much. I'd first like to thank the organizers for inviting me to this meeting and giving me this opportunity of giving a seminar here. The topic of my seminar, as you just heard, is perfect transfer of quantum information across graphs. I'm from the University of Cambridge, and the work that I'll present is essentially contained in 3 papers done with a host of collaborators, many of whom are here in the audience. So this is joint work with Claudia Albanese, Matthias Crostandl, who's here, Arthur Eckert, Tony Dorlas, Alistair Kay, and Andrew Landau. But since this is such an interdisciplinary meeting, and this is the first talk on quantum information, I thought I'd just take 2 minutes to give a very brief introduction to the field. As you all know, classical information theory is the mathematical theory of information processing tasks, such as storage and transmission of information. Now, quantum information theory is the study of how such tasks can be accomplished using quantum mechanical systems. So it deals with how the quantum mechanical properties of physical systems can be exploited to achieve, for example, efficient storage and transmission of information. So the underlying quantum mechanics leads to important differences between the 2 theories, and it often yields distinctively new features which do not have any classical analog. Just a word about the fundamental units. As you know, in classical information theory, the fundamental unit is a bit, which takes values 0 and 1. And in quantum information theory, it's a qubit. So it can be simply understood as a 2-level quantum system. And with every quantum system, as you know, there is associated a Hilbert space. So in this case, the Hilbert space, which I denote by H, is isomorphic to C2. And using Dirac's Ket notation for a vector, and keeping the analogy with the bit, we shall denote these basis states as 0 and 1. And I'll just consider them to be represented by this and this column vector. So the state of the qubit, unlike the state of the bit, is not just necessarily the basis state 0 and 1, but by the quantum superposition principle, we know it's given by any linear superposition of these basis states, where mod alpha squared plus mod beta squared is 1, complex numbers. So physically, what does this correspond to? So it can correspond, for example, to a spin state of a spin half particle, for example, an electron, in which case the 0 and the 1 would correspond to the downspin state and the upspin state of the electron. Or it could correspond to, for example, the polarization state of a photon, in which case, for example, 0 and 1 could correspond to, say, horizontal and vertical polarizations of the photon. So where is the information? The information is encoded in the state of the system. So if you want, for example, consider a quantum information source. That can be, for example, highly monochromatic laser, which emits individual photons. And so these photons then travel through waveguide, a fiber optic cable, and go to the other end. So that's this transmission of information that we'll be interested in. So coming to a more general situation then, quantum information is encoded in the quantum mechanical states of physical systems, and to each physical system is associated a Hilbert space, and the state of the system is given by a vector, which we denote by the psi, the state vector, or more generally, just by a positive operator of unit trace, that is the density matrix, acting on H. Now, an essential part of a quantum information, any quantum information processing task, would be the transfer of information from one location, say the location A, to the location B. So transfer of information means transfer of a quantum state from one location to the other. So here, schematically, I've just mentioned that these are the 2 ends of a quantum wire, where by a quantum wire, I just mean the fundamental unit of, say, a quantum computer when it's, if and when it's built. So this task of transfer of information is rather explicit in the scenario of quantum communication. Because in that case, the goal is to communicate information between two distant locations. But just to emphasize its relevance, it is also good communication of information is also essential between different parts of the interior of a quantum computer too. So what I'm just trying to say is that the thing that I'm considering in transfer of information is an absolutely essential feature. Now, so we want to give some measure of the quality of the transfer. How well have you succeeded in transferring the state? So the quality of transfer in a time t, I denote by the fidelity, which for this talk I denoted by modulus of ft. So let psi in A0, this ket, be the input state at this point A at time 0. And let psi b out t be the output state at B at time t. Then the fidelity, in a very simple way, is just the modulus of the overlap between this input and output states. It takes a value between 0 and 1. And when do we say that the transfer is perfect? If this fidelity is 1. And if it is 1 for some time t equal to t0, then we say there has been a perfect state transfer from A to B in time t0.
Ask a simple question.
Sure.
If you transfer information, you don't only transfer one bit, you want to transfer several bits.
Yeah, we'll come to it. We are just going in steps. So I'm going to start from a single qubit and end up with entangled states too. Okay. All right. So a few words about the mechanism of state transfer. So this depends on the nature of the system which is in the intervening space between A and B. So which we can call the quantum channel connecting A and B. So there are different ways of transferring the state. It can be transferred via, for example, individual information carriers, photons, phonons. And this happens, for example, when the channel or this medium intervening is an optical system or an ion trap, respectively. It can also be transferred via collective phenomena. In this case, the carriers are magnons or excitons. And this happens, for example, when the channel connecting A and B is given, for example, by an array of quantum dots or optical lattices. So such a channel can be modeled by what is called quantum spin networks. And what we consider in our work is perfect state transfer in a quantum channel modeled by a quantum spin network. So I have to tell you what a quantum spin network is. So a quantum spin network can be most generally described as a collection of interacting qubits. So these are, for example, these spin half particles on a graph G. So the graph is, as usual, given by a vertex set and an edge set. So this is an example of a graph. And these set of vertices of G correspond to the locations of the qubits. And EG are the set of edges of G which connect those qubits which interact with each other. And as you all know, to any such graph G, one can associate an adjacency matrix, which is a matrix which is 1, whose elements are 1, if the corresponding vertices are connected by an edge and is 0 otherwise. Now, there must be some, since each vertex is the location of a qubit, to each of these vertex, one can associate the Hilbert space C2, which is just a single qubit Hilbert space I introduced a while back. And it has basis vectors, which are these zeros and ones, and alternately move between the 0, 1 representation and the downspin, upspin representation. So the Hilbert space associated with the full graph is then just the tensor product of these on-site Hilbert spaces over these vertices in G, which is isomorphic to this. So here n is just the cardinality of the vertex set. Now, now about the dynamics. Something has to cause the state to transfer from one end to the other. It is true that in the beginning of the talk, I'm just going to talk, as Professor Milansky pointed out, only a transfer of a single qubit state, but hopefully come to the generalization towards the end of the talk. because the basic mechanism can be understood if you really understand the transfer of a single qubit state. So we consider the dynamics of the spin system to be governed by some suitable Hamiltonian, and we find it convenient to consider the XY Hamiltonian. So this is the expression of the Hamiltonian. So Hg is, of course, a Hermitian operator acting on the Hilbert space of the graph. So these sigma Ix, sigma Iy, and we'll encounter later sigma Iz, are simply the Pauli matrices acting on the on-site Hilbert space Hi. So these are 2 cross 2 matrices acting on this complex 2-dimensional Hilbert space. And Jij gives the strength of the interactions between the qubits which interact with each other. So it is the coupling strength between the ith and jth vertices. So let's start by considering what would be the method of transferring, what would be the steps if I wanted to transfer a single qubit state, say, from across a graph. So the first thing to do is, what is the entry point and what is the exit point? From where to where do we want to transfer the state? So let A be the, so you designate one qubit, say A here, as the input qubit, and another qubit as output qubit. Now you want to, say, transfer a single qubit state. So that state can be any arbitrary state. So it's an arbitrary state in the single qubit space, and we encode it in the qubit A. So the state of this qubit is the state that we want to transfer. So it's written in terms of the basis vectors of the on-site Hilbert space here. And all the other qubits are prepared, say, in the state 0, which is the downspin state. So the initial state of the full graph G is just this, psi G0. So A is in the state phi, and all the others are in the state 0, where phi is the encoded state, which we want after some time to end up here. So what happens? The idea is very simple. Time evolution of the graph under the Hamiltonian that we've chosen causes the state to propagate. And we know how the time evolution works. The Schrödinger equation tells us that the state of the full graph after a time t is just given by this. This is the time evolution operator. And so the next step would be that after some time t, I'll go into all the details later on. This is just a very brief outline. So say after a time t, we want to recover the state from B. So the state at B is just given by the reduced density matrix. So this is the pure state density matrix corresponding to the final state. And you trace over all the sites except B. So that gives you the state at B. And there is an expression for the fidelity, which reduces to the previous case when this is a pure state. And if this fidelity is 1, we say we have achieved perfect state transfer. So what you see is that it is the Hamiltonian which is the crucial thing, which is causing the information transfer from one end of the graph to the other. So let's spend 2 minutes on to study the effect of this Hamiltonian. Let's be very simple. Just consider 2 sites. Okay? And what does the Hamiltonian do? So what we find is this is if there are just 2 sites, the Hamiltonian is simply half sigma x1, sigma x2, plus sigma y1, sigma y2. So let us act on the state which is up in the first case and down in another case. So if you just calculate this, what you will find is it gives 0, 1.
I'll ask you again. Sorry.
Yeah?
You said the fidelity becomes 1 in the previous slide.
If it does become 1, then we say it's perfect
You
transfer.
don't start with an eigenstate, you don't finish with an eigenstate. So the population depends on time. So if it is 1 at time t, it can be half at times t plus epsilon.
No. It will not. Just give me a little more time, and it'll become clear why the fidelity can be 1. I'll go
It
through.
can be 1, but
No,
doesn't
this
it
is
time
not his
dependent?
point. This is not his point.
There is a certain time.
You choose the time, touch that.
Yeah, the question I ask, which is just given here in a minute, is that is there a time? And you're given a set of n qubits, and can you arrange it in some graph, and can you find a certain time for which the fidelity is? That is the question. Thank you. Yeah.
Specified with
Yeah. So the effect of the Hamiltonian, as we just saw there, is to swap the states of the spins at A and B. Therefore, state at A is transferred to the state at B. So now this is the question I was just stated. So given n qubits, how would you arrange them in a graph G so as to achieve perfect state transfer? I should have written over some time t, over the maximum possible distance, all right? So if you're given an n qubits, what would you do to get maximum distance? You would arrange them in a chain, right? Okay, so the distance is of course maximized for a linear chain. But see what happens here. If, say, you could switch all these couplings off, all right, a hypothetical situation, and then switch them on and off successively. So you get the states swapped, transferred from here to here, then from here to here. And so we could swap qubits one by one all the way from A to B. But this is most undesirable because such a dynamical control over the couplings is an experimental impossibility, almost experimental challenge. So let me modify my question a little bit and restate what our real aim is. So the aim is arrange, you're given n qubits, arrange them on a graph G such that perfect state transfer is achieved for some time t over the maximum possible distance, and no dynamical control is needed for the state transfer. And can we do that is the question. And the answer is yes. We are able to design two different categories of graphs or networks. And let me state what they are. But in order to state what they are, I just need to introduce the concept of a distance on a graph, which everybody here knows. But anyway, for completeness, given a graph G, with the vertex set and the edge set, we define the distance between any two vertices as the minimum number of edges in the shortest path between I and G. So if this is the graph, obviously the distance between I and J would be 3, right? So now that we have a concept of distance, let me call dn the maximum distance of perfect state transfer of a graph of n qubits. So the two categories that I said we can design can be distinguished by means of this quantity dn. So we'll go through both these categories in a lot of detail, but let me just state them here. So the first category is what I call unmodulated spin networks or graphs. So here what we have is, remember we have any possible graph, and these were the couplings, right, from A to B. And these couplings, say J1, J2, etc., are all identical. So every Ji is equal to Jj. And we can, in fact, even set them equal to 1. Okay? So the couplings are identical. In this case, for a graph G, which has n qubits, where n is of a particular form, 3 to the k. So this is, for example, a graph with 3 to the k, because this has 27 sites. In that case, you can show that for a constant time, and this time will turn out to be pi over root 2, you can achieve perfect state transfer between this point and this point, that is the antipodes of this cube. And so if you generalize it, this just turns out to be 2 log 3 to the n, log n to the base 3. So this is one category of spin networks, and I'll prove this result. But this is not much, so you want to consider better distances. And you can do better by making these couplings not identical, but by choosing them cleverly. So in fact, if you make a particular choice of these couplings, that you can achieve the maximum possible distance. You can take n qubits and transfer states over the full distance n. So you can have a linear chain for any arbitrary n. You have perfect state transfer in a constant time. Okay. Back to the Hamiltonian for a few minutes. Let's look at it, and we are going to make use of certain symmetry properties of the Hamiltonian. Firstly, notice that the state where all the spins are in the state 0, so the down spins, that is the 0 energy eigenstate of Hg. So all spins are down. Let me easily calculate it. And the Hamiltonian has a particular symmetry. The total z component of the spin is conserved. That means if you look at the operator, sigma z total, which is the sum of the sigma I z i's, where I is summed over all the vertices, then this operator commutes with the Hamiltonian. So as a result of this, the Hilbert space decomposes into invariant subspaces. And these invariant subspaces are the distinct eigenspaces of this operator sigma z total. So what I've done is I've listed some of these subspaces, and these subspaces are labeled by a particular eigenvalue of the operator sigma z total and corresponding configurations. So for example, the lowest energy eigenspace is S0, which corresponds to all spins down, for which sigma z total would have an eigenvalue minus n. We'll be interested in the next one. That's when one spin is up. This up spin could be anywhere here, but so that's why I wrote this is just one example of the corresponding spin configuration, and for which the eigenvalue of sigma z total is obviously minus n plus 2. And so on and so forth, and there's Sn where all are up. So in general, S small m would be one where m of them are up and the rest are all down. So that would be the m excitation subspace. Now, if we just consider the transfer of a single qubit state from a location A to the location B, you can see that the dynamics of the spin network is confined to the single excitation subspace S1. Now, I'll show you in a minute why this is true, because you start off with the state in the single excitation subspace, and these are invariant subspaces. I'll return to the point in a minute. But let's just spend a few minutes on this description of this subspace. So a basis state in this subspace corresponds to a spin configuration, as we saw, in which only one spin is up and all the rest are down. So such a basis state can be denoted by this J underbar. Whenever I use the notation underbar, that means it is a vector in this subspace. So here J belongs to the vertex set, and it is just the label of the vertex where the spin is up. So when I write J, I just mean it is the state which is a tensor product of zeros everywhere and 1 at the jth qubit, right? So it corresponds to such a configuration. So if you consider the ensemble of all these vectors, then they form a complete set of orthonormal basis vectors in S1. And obviously, S1 is an n-dimensional subspace because this excitation can be in any one of these n locations. Sorry? Okay. So when restricted to S1, now this is an interesting thing. When you restrict to this subspace, then Hg, written in this basis, is given by obviously an n cross n matrix. And this n cross n matrix turns out to be identical to the adjacency matrix. Now, so that's why it is because of this Hamiltonian being equal to the adjacency matrix that the time evolution of the spin system, in this case, when we are considering a single qubit state, can be interpreted as a continuous time quantum walk on G. So this was first considered by Fari and Gutmann in 1998. So what is a continuous time quantum walk? The easiest way to understand it is as a quantum analog of something we are all familiar with. That is a continuous time classical random walk on the graph. So how is it defined? So you're evolving something on a graph, but now it's a quantum walk. So what the underlying equation governing it must be a Schrödinger equation. And we consider it to evolve by treating the adjacency matrix as the Hamiltonian. So the quantum walk on G is determined by the unitary operator e to the ITAG. So you see, this is precisely the scenario we have arrived at by restricting ourselves to the single excitation subspace. So suppose you start off, the walk starts off on the vertex I, so at the time 0, then the probability of finding it at the vertex J is obviously given by this, where this is the time evolution operator. So the purpose of this transparency is to draw a relation between the perfect state transfer and a continuous time quantum walk. And we'll come back to this in a while. Okay, now let's proceed with the transfer of a single qubit state. And let's be very simple. Simplify our graph just to a chain. Okay, just to a simple chain. So this was the scenario. This is the state we want to transfer. We've already encountered this. We encoded it in this qubit. All the others are in state 0. As we saw in a previous transparency, the initial state is then given by phi at A and 0 everywhere else. So if you just substitute for phi, what do we get? We get one term which is alpha, A being in the state 0, and so all the others, plus beta, A being in the state 1 and 0 everywhere else. So we can use the notation that we've just introduced, because this is nothing else but the 0 energy eigenstate. And this is nothing else but the state 1 in the single excitation subspace. Now what do we want to do? So this is the state. We want to evolve it under the effect of the Hamiltonian. Now what happens? 0 is a 0 energy eigenstate. So it remains unchanged. It doesn't even pick up any non-zero dynamical phase factor. So we can essentially forget about the 0. What does 1 do? 1 is in the single excitation subspace. So, and this is an invariant subspace. So it must evolve into some other state in the same subspace. So what we are looking for is something like this. We started off with alpha 0 plus beta 1, and it evolves in time t to alpha 0 to some 1 evolves to a state which must again be expressible as a linear combination of the basis states of S1. And I introduce a t here because there's this dynamical phase factor which can be picked up in this time t. So this is what's happening. And I want to know whether there is a perfect state transfer from A to B in some time t. So for that, what do we essentially need to do? We need to find the probability amplitude of this 1, which is the state with 1 at A and 0 everywhere else, to evolve in time to the state n, which is 0 everywhere else and 1 at B, right? Because then you go from A to B. So that's why I'm focusing on the single excitation subspace. Now you'll see why I chose the XY Hamiltonian. So what you're looking for is this probability amplitude. Start with the state 1, evolve, and take its overlap or the scalar product in a product with n. And if the modulus of this quantity, this is the fidelity, is 1, then we say perfect state transfer happens. So now let's say, I said there are 2 classes of graphs. So let's move to the first class, which I said was the unmodulated graph or spin chain of n vertices. So here the interqubit couplings are all identical. And the Schrödinger equation is exactly solvable for this Hamiltonian. And that's the reason for choosing, one of the reasons for choosing this Hamiltonian. So this is the time-independent Schrödinger equation. We can solve it exactly, and we can find explicitly its eigenvalues and its eigenvectors. Don't worry about the exact forms. And if we know the eigenvalues and the eigenvectors, we can obviously calculate the probability amplitude. And in this box, I've written this explicit expression for the probability amplitude. And here comes something interesting. So what we find is, let's put just n equal to 2. That means just 2 sites. Here ft reduces to something as simple as this. For n equal to 3, it reduces to this expression. So what do you see? These are periodic functions of time. So what we find is this. Sorry, don't generally cover. So ft is periodic for n equal to 2 and n equal to 3. So therefore, just looking at this, we see that there is perfect state transfer for t equal to pi over 2 for this case, and t equal to pi over root 2 for this case. Okay, so what we have arrived at is that we have just considered these 2 very simple scenarios. One, a graph with 2 sides, a chain with 2 sides, one, a chain with 3 sides. Here there is perfect phase transfer in this constant time, pi over 2, and here pi over root 2, from one end to the other. So the next question you'll ask, what about n greater than equal to 4? Is there any time t for this linear graph, this linear chain, for which there is perfect transfer? And the answer is no. And I thought, since I have a lot of time, and well, hope so, this is an interesting result which is very easily understandable. So let me just give you the proof of it. That is because one can find a necessary condition for perfect state transfer of a single qubit state across a graph. I've used the word mirror symmetric just because the condition that I'm saying is not only applicable for the linear chain that I'm talking about, but would be applicable for any graph which has a mirror symmetry. That means the graph looks identical from the point of view A or the point of view of B. So the condition for if the graph is to allow perfect state transfer in any given time t, then it must satisfy this condition, which is a nice condition because it is entirely in terms of the eigenvalues of the adjacency matrix. So you see there's the adjacency matrix of the graph, and EI, etc., are the eigenvalues of this matrix. If the ratios of their differences is a rational number, then it allows perfect state transfer, otherwise not. Now this is very simply understood. So consider a mirror symmetric graph. So let A be the initial state and B is the final state. So A is, for example, as we saw, 1 at A and 0 everywhere else, and B is 0 everywhere else and 1 at B. So say G, the graph that we are considering, for example, just this one, is capable of perfect state transfer in a given time t0. What does that mean? That means when the time evolution operator acts on A, it gives B, say modulo a harmless phase, e to the I phi. But you see, mirror symmetry tells us that A and B are entirely equivalent, right? If you look from the graph from A, it's the same as if you look from B. So we had arrived at this equation, e to the minus ITHG, A gives this. But let's now evolve it for another time, interval t naught. So now an extra time t naught, so 2 t naught. So that's just e to the minus IT, this acting on what you've got before. But you see, if over time t naught you've come from here to here, by mirror symmetry, the next time t naught you'll come from here to here. So you'll get 2I phi A. Thus the system is periodic up to a phase factor 2 phi with a period 2 t naught. Okay? So what do we conclude? That a mirror symmetric system, for example, a linear chain, must be periodic if it is to allow perfect state transfer. So in other words, you can just write it that it must satisfy this. This is the initial state. If you evolve it for a time 2 t naught and take the scalar product with the original state, then the modulus must be equal to 1 for some time t0, finite time, and that is the time for perfect state transfer. Right. So now let us understand this condition in terms of the adjacency matrix. Now that's very simple because the initial state, A, let us call it psi 0. So this is some state, right? It can always be expanded in terms of the eigenstates of the Hamiltonian. Now what are we saying? We are saying that it has to be periodic with a period 2 t0. So let's look at the psi after our time 2 t0. So what is this? It's just the state got by acting on this by this evolution operator. But since this is our energy eigenstates, the only effect of this is to pick up the factor Ej, the energy. But what do you see? This is nothing else but e to the minus I 2t. This we know, this quantity must be equal to e to the 2I phi psi naught. Why? Because we said that the system is periodic up to a phase 2 phi with a period 2 t0. So that's just what I've written. And I've written that out, psi 0 is just AJJ. So if you just look at this, look at these two lines, what do we conclude? We conclude that 2 t naught EJ minus 2 phi must be equal to 2 kj times pi, where kj is an integer.
But I'm sorry, you assume that all AGs are non-zero?
Yes. You assume that AJs have to be.
No. We consider those values of j and j prime such that the denominator does not vanish. That's the condition I'm giving.
AJ has to be unequal to 0 in order to make this. AJ has to be non-binary.
AJ or EJ?
AJ. AJ has to be unequal to 0.
EJ.
AJ.
AJ. Oh, AJ. Sorry. Yeah. So AJ. Yes, AJ are just the expansion coefficients.
Yes, but they have to be different from 0 to make this conclusion.
Some of them can be 0.
Some of them can be 0.
If the eigenfunction vanish at that point.
If the
The eigenvector vanish at the point A, which is possible for some graphs.
all right. Okay, I'll give that a little bit of a thought. Let's talk after the seminar. Well, for the time being, assuming this to be as it is, what we find is eliminating phi from two of these equations and then eliminating T naught, you just get the ratio of the differences is just the ratio of two integers, which is a rational number. And what we find is that was a very clever work by Matthias Christandl, who's there here in the audience, showed that for n greater than equal to 4, this condition is not satisfied, and that's the reason we do not get perfect state transfer. So let's move on to higher dimensions now, right? Because this is not very good. Just getting perfect transfer over 2 sites or 3 sites is not very desirable. So let's consider taking n-fold Cartesian products of these two, considering these to be the initial building blocks. So if this is G, we consider G cross G or G cross G cross G. Right. So what we are doing is taking d-fold Cartesian products of the original building blocks for which we have explicitly proved perfect state transfer. So let GD be the d-fold Cartesian product. So if 1, 2, 3, this is the G. So this is then our G cross G. And we consider the transfer between these two antipodes, which would then have coordinates with all 1s and all n's. So these are the two antipodal vertices of GD. So if psi k and psi l are the eigenvectors of the adjacency matrix of the graph G with the eigenvalues ek and el, then what you can show, just some very simple graph theoretic calculations, that psi k tensor psi l will be the eigenvector of the adjacency matrix of G cross G, corresponding to an eigenvalue which is the sum of the two eigenvalues. So this allows us to prove something very simple, that we are now moving on to higher dimensions. We started with these two building blocks. We built graphs which are d-fold Cartesian products of these two building blocks, either this or the one with 2 sides. And we proved that the fidelity of state transfer for this graph in higher dimensions is simply the dth power of the fidelity of the original graph. And this we've already computed. So you see, this allows us to give the fidelity for the larger graph. So this is what happens. We get a result almost for free. For a d-fold Cartesian product of this graph, we call the graph a one-link hypercube. It is simply a cube. The fidelity of transfer between the two antipodes is given by this, because we know that FGT, we calculated it to be sine t. So once again, we see we get perfect state transfer for a time t0, which is a constant time equal to pi over 2. Similarly, if you consider the hypercube, which is built out of this, then the fidelity is simply this quantity, which is the dth power of the modulus of this. And here too, t0 is pi over root 2. So once again, we get a perfect state transfer for a constant time. So a single qubit state can be perfectly transferred between the two antipodes of a one-link hypercube and a two-link hypercube, respectively, for any dimension d. And that's interesting. So just to show you a picture, this is what, because I can only draw a picture in 3 dimensions. For a one-link hypercube, you can send the state perfectly between a to b in time pi t over 2. for a 2-link hypercube with so many sites, that is 27 sites, you can send it between this and this in a constant time. So for dimension d, for a 2-link hypercube, n is 3 to the d. That's the generalization. Okay, this is 3-dimension, that's why it's 3. So that's why I wrote in the beginning when I introduced the 2 sets of classes that the maximum distance of perfect state transfer is 2 log n to the base 3. Because look at the example here. Here n is 3 to the power 3. So dn is this expression, which is 6, and which is right, because the distance between a and b is 1, 2, 3, 4, 5, and 6. Okay. Now, this has some interest. This result is interesting because we saw before that the transfer of a single qubit state can be understood as a continuous time quantum walk on GD. Now, always we are wanting to compare the quantum and the classical case and see what differences arise. So therefore, the minimum time t0 for the perfect state transfer that we just found, the pi over 2 over pi over root 2, it is nothing else but the mean hitting time for a continuous time quantum walk starting at A and going to B across this graph GD. So the classical analog of this quantity is the mean hitting time of a continuous time classical random walk starting at A and going to B. And that can be seen to be something very different in the sense the leading term is 3 to the D here and 2 to the D. So the difference is that this grows with the dimension, whereas this is totally independent of the dimension. So this is a constant for any D. So that's why the quantum walk provides an exponential speed up over its classical analog. Okay, now to the second class. Still, we haven't achieved really a huge distance. We've achieved a mathematically curious result that the transfer over any arbitrary dimension d between the antipodes of these special hypercubes are totally independent of the dimension as opposed to the classical case. But now let's try to do better and consider longer distances. What we now do is consider a chain back to a chain, but now the couplings are not all identical. Okay? So once again, we are still considering a single qubit state transfer. So in the single excitation subspace, Hg, if you write it out as a matrix, it just looks like this. Okay? So the question that I'm asking in the second part of this talk is, what are the values of these couplings J1, J2, etc., for which both single qubit states and entangled states can be perfectly transferred between the two ends of this chain, A and B. Okay? And n can be arbitrary. Now, the answer to this question comes from a curious correspondence. It comes from the following correspondence. The n-qubit spin chain in the single excitation subspace can be put in correspondence to a fictitious spin S particle. All right? This may seem strange in the beginning, but I'll show you that it is not strange. So consider just a fictitious particle with a spin S, which is related to this n by n minus 1 over 2. So what you can see is that these basis vectors in the single excitation subspace, which I labeled by J, now remember J was the site where the spin was up, can be put in one-to-one correspondence with the basis vectors we are used to, these angular momentum basis vectors, where m goes from minus s to plus s. So how are we doing this? What do I mean by this? We are essentially, all we are doing is relabeling the qubits. So this was my chain. Let me consider a simple example. Suppose n equal to 6. So s, which is given by this expression, is 5 over by 2. So before I was calling j, could be 1, 2, 3, 4, etc. Let's put the corresponding values of m. It will go from minus s to plus s in steps of 1. Okay? So that's what I'm going to do. My basis vector 1, I'm going to put in correspondence to s minus s. And this n to ss. So in general, what I'm going to do, I'm going to relabel the basis vector j by sm, where m is given by this expression. Now, why am I doing this? That's because you have a problem, hard problem, but you're showing that it's equivalent to a different problem which is more easily solvable. And so you're going to use the solution here to find the solution there. That's the usual trick. So we have introduced a fictitious spin S particle. We've drawn a correspondence between basis vectors in S1 with the angular momentum vectors Sm. We know the Clebsch-Gordon coefficient, and we know how to deal with these angular momentum vectors. So now consider a Hamiltonian to govern the fictitious spin S particle. Suppose it is something like this. Lambda is some constant, and Sx is the spin angular momentum. So we know how Sx acts on these vectors Sm. So it either raises or lowers, and you know the corresponding coefficients from our initial quantum mechanics text. So what you find, interestingly, and this is where the correspondence comes from, if you take the representation of this Hamiltonian, Hp, of this fictitious particle in this basis Sm, then it looks exactly identical to the Hamiltonian of our spin system in the single excitation spaces, where the J's are now given by this quantity. You see? So that's the correspondence. And how does it help us? If you consider the time evolution of the spin chain in S1, the time evolution operator can be then, these two are identical, so you can just replace it by lambda Sx. So now, if you want to consider the fidelity of the state transfer from A to B, what we can do, so we need to compute the fidelity of state transfer from A to B of the spin chain. So you start from 1, you act on by this evolution operator, and take the scalar product with n. But we have mapped 1 to the state S minus S in the angular momentum representation of this fictitious particle. And we've shown that this Hamiltonian is the same as the Hamiltonian of this fictitious particle. And the good thing is we know how to compute this quantity explicitly. And we can compute it, and lo and behold, this is the value that we find. So what do we see, therefore? That the modulus of ft is once again equal to 1 for t equal to pi over lambda. So for a spin chain or graph of n sites, where n is absolutely arbitrary, if you choose the couplings to be this, then perfect state transfer of a single qubit state occurs in a constant time. Now let me just tell you that this result is not in conflict with what we got before, because if you just consider capital N to be equal to 2, so here capital N equal to 2, right? So there's only one coupling, J1. So according to here, we get J1 equal to lambda over 2 square root of small n, so n is 1 because we are looking at J1. So it's 1 times 2 minus 1. So it is simply lambda over 2. Okay? Now when we first talked about these graphs, we had considered all these j's to be equal and identical to be equal to 1. So if we put J1 equal to 1, we simply get lambda equal to 2. Then look at the time of perfect state transfer. It is pi by lambda, which is simply pi over 2, which agrees with what we got before. So this is just an agreement, but it is a much stronger result because we can go to any length n at all. Okay, so now you want to do something more than just a single qubit state. Actually, forget the first line. What we prove is something stronger. You not only get the state, single qubit state transferred from here to here, but you can also get a single qubit state transferred from here to here, here to here, etc. So you see a mirror symmetry. So what you prove is that not only does 1 go to n, but 2 goes to n minus 1 modulo a sign, 3 goes to n minus 2, I think this should be a plus sign, etc. So as a consequence, now you can move away from a single qubit state to a perfect transfer of an entangled state in S1. How would that happen? So suppose now, you once again have the graph, but instead of inputting just a single qubit state, you have an entangled state of these two qubits here. So the encoded state is now encoded in the qubits 1 and 2, and it is this entangled state, 1, 0 plus 0, 1. And all other qubits are in the state 0. So the initial state is phi of 1, 2, and 0 everywhere else. So if you substitute for phi, what do we find? It is 1 at the state location 1 and 0 everywhere else, or 1 at the location 2 and 0 everywhere else. So the state is 1 over root 2, 1 plus 2. Now what happens? You have one plus 2 is the state that you want to transfer. What will happen after a time phi over lambda? Using the result that we just found, we know that 1 will go to n, and 2 will go to minus n minus 1 in this time. So let's write these out. This is just zeros with 1 at the location n, and these are just zeros with 1 at the location n minus 1. So just a little bit of inspection will tell you, you can rewrite this at zeros in the first n minus 2 qubits, and this entangled state in the last 2 qubits. But this is with the wrong sign, right? We started with a plus. But that is easily correctable by a local unitary. We just act on by a sigma Zn, because a sigma Zn, according to my choice, when it acts on 0, gives us a minus. So that corrects for the sign. So what you end up with, you had started off with phi in the first 2 locations, an entangled state. Now you've ended up with a phi in the last 2 locations. So you have achieved perfect transfer or of an entangled state in S1 in a time phi over lambda. This leads us obviously to the next question: what about higher excitation subspaces, more than the single excitation subspace? I will not go into the details of this, but except tell you an interesting anecdote. One of the collaborators is Claudio Albanese, who used to do mathematical statistical physics, as I used to do, and then he's now moved to mathematical finance. And I was just talking about our work on state transfer when he was visiting here to give a talk in finance. He got interested and then sent me an email while he was traveling through Heathrow Airport saying, I use certain things in option pricing which you might find helpful. And this is what they use in option pricing, and that allows us, strangely enough, to prove this rather interesting result of transmission of entangled states in higher excitation subspaces. So the fact is, the result is not just perfect transfer of a state, a 2-qubit or a 3-qubit state. You can get something stronger. What you can get is actually a mirror inversion of a state. So I'll come back to this. This is the picture in simplistic terms that you can achieve. Suppose you have all this, a linear chain once again, everything is in the downspin state, and you have some state here. So after a certain time, capital T, the whole state gets mirror inverted, so it ends up here. So this mirror inversion results once again from the time evolution under a suitable Hamiltonian. And the Hamiltonian, once again, is the Hamiltonian we had, the XY Hamiltonian, but with suitable on-site magnetic fields. And we have a liberty in choosing what these Hn and Jn's are to ensure that what I claim really happens. And these are chosen such that the eigenfunctions of this Hamiltonian in this mth excitation subspace are given by certain discrete orthogonal polynomials which are used in option pricing, which is, for example, Kraft-Tube polynomials or Raka polynomials. Anyway, I won't go into that, and I'll end with my last transparency. Just to conclude, So very first of all is acknowledgements to all my collaborators, and these are the references of the papers which contain the body of the work I presented, and credit is absolutely due to S. Bose too, whose paper in Physical Review letter that I quote there led us to the study of perfect state transfer. There has been a lot of related work, and I can't give a list of all, but I'd like to point out just one of these, and especially Alistair Kaye's PhD thesis. He's now a postdoc here. So to summarize, this is what I talked about. Perfect transfer of a single qubit state across a spin network without the requirement of dynamical control over interqubit couplings. showed that this is possible for two classes of networks. One was unmodulated spin networks, where the interqubit couplings are identical, and you get perfect state transfer across the antipodes of hypercubes, which are built out of a one-link or a two-link chain. And these times for perfect state transfer are constant and independent of the dimension. And T0 is the mean hitting time for a quantum walk on GD. Therefore, we see, if you compare it with its classical analog, we get an exponential speed up of the time taken. And then we moved on to engineered spin networks, where by suitably choosing the couplings, you can get perfect state transfer in the single excitation of single qubit states and entangled states over, once again, a constant time, which was this pi over lambda, which is independent of n. So you can get perfect state transfer over arbitrary distances. And I briefly mentioned higher excitation subspaces and mirror inversion too. Thank you very much for your attention. And I'll look into the question that you raised, but it just requires a little bit of thought. Yeah.
Yes, that's a kind of analogy. If you take it's a continuous analogy. If you take the sphere of dimension 2, it's a round metric, okay? And you look at the wave equation at time pi, if you start with some initial data which is near the south pole, at the time pi it will be near the north pole, exactly the same. So it's very similar, and you can look at that from point of view of special function orthogonal to
Yes, yes.
So your thing, it seems to be a kind of discretization of
Yes,
that
exactly.
for solutions which are
Yeah,
invariant by
because we are considering a discrete state space, a discrete phase. Thank you.
just a kind of analogy.
I have a question. You see, the whole concept is not clear to me. You tell me that you want to transfer information from A to B. Okay. For that purpose, what you have to do is, first of all, to put all the spins on the chain.
Prepare it in the ground state.
Well, I have to prepare, that's the point. I have to prepare it. So I already have to be in B in order to prepare B in the ground state, or it's 0. So why do I have to make the transfer? See, I'm already there.
Oh, no, but
Infinito. It's a practical question.
yes,
Why
but
do I have to transfer information if I already have to be there to put it to 0?
Local preparation.
Uh,
Local preparation.
yes. So suppose B is with a person which we have these two personalities, right? Alice and Bob. So B is with Bob, right? So all right. Let us make it this way: that this is a full chain. Right? No, listen to me. I'm answering your question. So if Alice is here, and say, consider the scenario that Alice has access over these sites, and Bob has access over all these. So they just say, all right, Alice tells Bob, we prepare everything in the ground state. So he prepares these to be in the ground state, and she prepares this. But Alice cannot access this.
But there is a phase relay.
No, they're all in the ground state, an absolute ground state. And now Alice encodes her state into A, and gives Bob the signal, time starts counting now. And so after that particular time, you pick it up. Sorry, these are mathematical work. I'm not saying I can do it in an experiment.
No, I just
so, but you see, it will make sense.
Mathematical question. What happens? You see, you are talking about bosons or fermions. What about the Pauli principle in all this business? It restricts your space.
No. Pauli principle doesn't occur because the spins are fixed. So the spins are not moving from one place to another. That's the whole idea. So there is no statistics coming in here because it's a quantum spin system, not a quantum lattice gas. You see? Because that's the whole idea. The spin is not bodily moving.
We'll probably have to finish this.
Okay.
Locations after